The 2025 Nobel Prize in Physics went to three physicists, John Clarke, Michel Devoret, and John Martinis. They were honored for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. In other words, they were the first to experimentally show that hallmark quantum effects, tunneling and energy quantization, can occur in the macroscopic world. Why does this matter? The answer lies in the quantum world. Quantum mechanics originally governed an unseen world, the realm of particles too small to observe directly. In that realm, a single particle can exist in multiple places at once. That's because a particle's position isn't fixed. It is spread out probabilistically according to the Schrödinger wave equation. One hallmark consequence of this is quantum tunneling. Even without enough energy to surmount a barrier, a particle can still be found on the far side, as if it had passed through the wall. In 1928, physicist George Gamow introduced the concept of quantum tunneling to explain alpha decay, showing how an alpha particle can probabilistically escape the nucleus despite lacking the energy to overcome the barrier. Remarkably, the tunneling probabilities he calculated matched the measured half-lives of radioactive elements. It was compelling evidence that quantum tunneling is real. And in 1981, with the invention of the scanning tunneling microscope by Gerd Binnig and Heinrich Rohrer, humanity was able to observe quantum tunneling directly for the first time. However, all of this had been confined to the microscopic world of single electrons. Most people assume that quantum mechanics holds at the atomic scale, but probably not in the macroscopic world. But that's a bit odd. If quantum mechanics is truly universal, then not just a single electron, but an entire current, made of billions of electrons, should be able to tunnel as well. This is macroscopic quantum tunneling. At first glance, it sounds impossible, yet the laws of physics we've uncovered suggest it could, indeed should, be possible. Scientists found a clue in a material called a superconductor. In a superconductor, when the temperature is driven extremely low, electrical resistance drops to zero. According to the BCS theory published in 1957, electrons then move in bound pairs called Cooper pairs. The many Cooper pairs formed in this state become phase coherent and move together like one enormous wave. As a result, a state emerges in which current flows without energy loss, the superconducting state. In 1962, physicist Brian Josephson predicted that if an extremely thin insulating layer is placed between two superconductors, Cooper pairs could tunnel even in the absence of an applied voltage. This phenomenon, now known as the Josephson effect, was soon confirmed experimentally, and Josephson received the 1973 Nobel Prize in Physics for the discovery. His discovery pointed the next generation of physicists toward a new line of inquiry. If a single Cooper pair can tunnel, could an entire current made of billions of Cooper pairs tunnel as a single macroscopic wave? In the early 1980s, three physicists, John Clarke, Michel Devoret, and John Martinis, built a palm-sized superconducting circuit and operated it at millikelvin temperatures. At its heart was a Josephson junction, with one crucial twist. They biased the circuit with a precisely controlled current. When the current is nearly zero, the junction's potential energy landscape takes the form of a symmetric potential well, trapping the particle in that well. As they applied a tiny bias current, the curve began to tilt to one side, like adding a slope to the graph. This is called a tilted washboard potential. As the current increases, the slope grows steeper and the system effectively slides, letting the current run freely. But the team applied an extremely small, precisely controlled current. In that case, the potential is tilted, but a pit-like barrier still remains. Without enough energy to surmount it, the current shouldn't flow, at least according to classical physics. Yet the team observed a striking result. At temperatures near absolute zero, where thermal fluctuations are essentially gone, the circuit suddenly began generating a voltage on its own. With no external trigger, the particle trapped in the pit crossed an otherwise insurmountable barrier. And it wasn't a single electron or a lone Cooper pair. Billions of electrons, acting as one giant wave, passed through the barrier. It was decisive evidence of macroscopic quantum tunneling, showing that the laws of the quantum world can operate not only microscopically, but on macroscopic scales as well. It didn't end there. The team found another strange phenomenon inside this circuit. In ordinary electrical circuits, energy changes continuously, but this circuit had only discrete, step-like values, like the energy levels of electrons in an atom. The researchers realized that this electrical circuit, vast compared to an atom, was behaving like an artificial atom, sharing the same quantum states. This discovery later laid the foundation for superconducting qubits. The core idea behind quantum computing, billions of electrons act as one coherent wave, putting the device in a superposition of 0 and 1. The 2025 Nobel Prize in Physics appears to have recognized precisely this. But to me, this wasn't just an award for the technology behind quantum computing. It's a tribute to a fundamental experiment that opened the era of quantum technology, an applause for a bold challenge that shattered the long-held notion quantum phenomena exist only in the microscopic world. And that applause will ripple through space-time, carrying forward into the future. Just as BCS theory led to the Josephson effect, and the Josephson effect to macroscopic quantum tunneling. As one of this year's laureates, John Clarke has reflected, they never imagined, 40 years ago, its impact would reach this far. Perhaps on that day, what fell wasn't just a barrier in a circuit, it was a wall in our understanding.